All right, welcome to the Special Young Investigators Semi-plenary talk. It's my honor to introduce Michael Tupek from Sandia National Laboratories. I'm Joe Bishop, also from Sandia National Laboratories. I've worked with Mike for several years, and I remember distinctly when he started at Sandia and being extremely impressed. So it's my honor to introduce him. He got his BS degree at the University of Wisconsin at Madison, got his PhD at MIT in 2013. He joined Sandia directly after graduation. For the past 6 years, he's been the lead software developer for the Sierra Mechanics Multiphysics Finite Element Code Suite. This code is widely used by hundreds of analysts across both the Department of Defense and Department of Energy. His work lies at the intersection between computational mechanics research and production needs of Sandia's finite element codes. Mike has a variety of research interests and ongoing collaborations with academia. His research interests include various methods for modeling fracture and failure, much of which he'll be talking about here shortly, mesh-free methods, inverse and adjoint-based sensitivities for nonlinear mechanics, high-performance computing, and of course, machine learning. So, Mike?
Let's see if this works. All right. Thank you, everyone, for coming. It's a real honor. Thanks, Joe, for the introduction. This is a humbling invitation to do this, so I'm glad that people came. And it's also good to see that there's a couple people not doing machine learning, so they came here. That's good. So this is just a generic Sandia template. So I wanted to start just by giving like a little bit overview of kind of why Sandia, or like the kind of things that we care about Sandia. And one of them, of course, is modeling fracture. So I'm going to start with very controversial statements on the definitive state of the art on fracture modeling. Okay, so I'll get in trouble here. But okay, so one thing that Sandia does is Sandia sets up these fracture challenge problems. They've been doing these for, I don't know, almost 10 years probably. And what they do is they do some experiments on some metal, and they give that to an analyst. And then the analyst is supposed to use that to calibrate their material model, use whatever their favorite method is, and then make predictions on a new geometry with a new condition, and just see how well people do. So these are the three external ones that have been opened up to the community. There's been some additional internal ones that we don't let anyone know about. I think that's not quite true, but the three that we've opened up to the community. And so I just wanted to sort of highlight sort of what you need to do in order to get these things right, just to start, just for context. So here is the most recent one. This is sort of an additive manufacturing one where they gave these coupons of metals and they tested it in various tension, and the analyst was asked to calibrate the material model to this, and then make a blind prediction about a different geometry. And so this is the result from this team from California. So I think maybe 4 of these guys are probably in the audience judging me for explaining their work incorrectly. But the takeaway here is that they were able to very successfully, in this case, predict the response on this new geometry. And what this involved was a lot of very careful calibration, rate, strain rate, temperature dependence. Sometimes these problems require anisotropy, and just really getting the mechanics of the sort of plasticity model correct. So those details mattered a ton. And so in terms of the method they use, state of the art, element deletion, okay? And so element deletion is sort of the common word. At Sandia, we call it element death because we're a little bit more morbid. There's some commercial companies which will remain unnamed, which call it element erosion in order to make it sound a little more scientific. So by far, this is the most successful approach in practice. And it wins, whatever that means, the Sandia Fracture Challenge year on and year again and again and again. And whether it's Sandia participants in this contest or external people, element death is almost always the winner. And why is it so good? Well, it's calibratable. You can calibrate it. It's very fast, so it runs on our parallel clusters, and it can handle all sorts of kind of material models. Let's see if I can get the video to play. I can't without going back up there. A flaw in my plan. So here's an example of, this is one of the calibration tests and the simulation done by the group I just mentioned. The video was processed by Kevin Mankdalo. And you can see, element death, elements are eroding or going away, but they're capturing sort of the mechanics. They're getting this cup cone behavior, which is pretty hard to capture in general. They've embedded the right mechanics. Okay, so why do we not like element deletion? Well, it's not conservative. We're deleting elements, we're losing mass and momentum energy. It's not convergent. If I refine the mesh, you're not going to get the same answer. So you have to sort of calibrate this to a mesh size and hope it extends out. But nevertheless, this approach is very predictive, right? It's been the most successful approach in terms of fracture modeling. Okay, so with that in place, now that I've fully motivated why we don't care about convergence, I will now explain a bunch of approaches that Sandia has been exploring to get convergence in fracture modeling. So there's a lot of alternative methods for doing fracture modeling, and I'll cover sort of the first two a little bit. The first one goes back a while, since the late 80s, I think. Field regularized, so this includes nowadays phase field modeling, but sort of previously gradient damage or non-local damage or gradient plasticity and the like. There's also mesh-free approaches, RKPM, element-free Galerkin, paradynamics, lattice particle methods. And these are sort of examples of these on the bottom here, right? You have a sort of smear damage here, you have particles bouncing around here. And then the last one, of course, which Professor Duarte talked about yesterday, explicit crack tracking. So these things are GFEMs, and Frank 3D is a code that does this. And I put cohesive zones in there, although it doesn't perfectly fit, sort of in the same spirit of having explicit crack. And so these approaches have been very successful as well, but they sort of more focused on brittle to some extent, although there are extensions. And so we're exploring these other ones just to see kind of what they can do for us, but we are also investing in the other one as well. So I don't want to be too biased. But okay, so regularized fracture modeling. So first I'm going to give a little quick summary of what we can do. There's going to be a hierarchy. We're going to go from brittle to quasi-brittle to ductile and then to sort of large deformations. That's kind of how I'm structuring this. And so we'll start with this, with what we do to regularize brittle materials. And this is sort of the classic phase field method. A lot of people may know about this. And so the idea here is that you have a Griffith material model, in which you have a volumetric strain energy, which is classical, and you have a surface energy term. So you have an energy which is dissipated, which is proportional to the area of crack as it propagates. So discretizing this is challenging. There are ways to do it, of course, through explicit crack representations, but XFEM, GFEMs, et cetera. But the philosophy in phase field is that we're going to give up on the complications of integrating over a surface where we don't know where it is yet, and instead replace that surface representation with a damage field or a phase field. And when we do that, it turns out that you can replace this surface integral with a volume integral over the damage with a length scale, L. So this length scale, L, tells you sort of how much you have a sharp crack on the left here, and the phase field crack is smoothed over a length scale L on the right. And in the limit, as L goes to 0, you recover a Griffith fracture. And so this is the idea of phase field. It's pretty common these days. Goes back before the citation I have here, so apologies. And so this is just to show that this makes sense, this works out. And so Professor Bourdon and Hossein in 2014 did this experiment where numerical experiment where they try to propagate a steady growing brittle crack. And they show basically that the input G sub C, which is 1.5 in this case, is captured by essentially moving this. You can drive this crack along and compute J integrals, and you do in fact get the 1.5 input G sub C that you expect as you go along. Another thing that we've done is that there's experimental results by Sandians where they have this problem with a glass and a metal which are bonded, and you cool the metal, and so the metal cools and you sort of get this crack which starts here to run and turn along the interface. And so we're able to capture that phenomena with these brittle phase field models. So there's lots of more results of this out there. This is a popular field, of course. And there's a lot of challenges remaining, but I won't cover any of them, but they've been covered in many other talks here today. So one thing I want to focus on is this idea of going to quasi-brittle. Quasi-brittle adds some interesting challenges to phase field modeling. So when you think about, one way to think about cohesive zone modeling is that you have a fracture process zone. So you have, say, some metal with some inclusions or something, and then you sort of in the wake, you have a traction-free condition. There's no stress across that interface. But then there's a zone where things are sort of starting to break apart. And so you don't have the full strength of the material, but it's not zero either. And so you can characterize this in the sort of simplest way by a traction separation law, whereas you open the crack more, you're decaying the traction on that interface until it opens up. And what you find is that if you do the scaling, you'll find out that there's a length scale called the fracture process zone size, which is sort of how long in front of the crack is it still sort of partially bonded, okay? And so you can think that's kind of like where there's like some glue or something where it's kind of still peeling apart. That's the process zone size. And so in some sense, this is the model that we want to do. We want a cohesive model. But what's well known and this was very popular maybe 8 years ago, is to do sort of inter-element cohesive zone modeling, where you take a bunch of elements and you put cohesive elements between each of the interfaces, and you run a simulation, because this is what you want. You want a cohesive response for these kind of materials at some level. But this is known to be very mesh sensitive, because now you've used the mesh to bias where the path goes. And so it's not convergent. And so people are, there's still strategies to alleviate this, but for the most part, I think people are trying to move to new approaches. So phase field comes in. Okay, so some people say, okay, we can use phase field. So phase field has a length scale, right, that we're smoothing over. And that induces basically a critical stress. So if you change the length scale, if you drop it, your critical stress goes up. So what you can think about doing is tuning the critical stress by choosing the appropriate length scale. And so that's one way you can think about doing sort of cohesive zone type modeling in a phase field setting. But this has some limitations. And so what's happening effectively is that you're tying, because these two things, the phase field length scale and the process zone size in these models, they scale proportionately to each other. So what that means in this picture, the regularization is kind of in Y. That's how much we're smoothing the crack. And then the front of the crack, what Nicholas Moyes has once told me is the nose, which is the part that sticks in front of the red. The nose will make more sense in a couple slides. They're kind of the same length, okay? So what we want to do is we want to break those two apart. We want the process zone size, which is the nose in front of the crack, to be separate from how we're regularizing it. Another way of explaining this issue is that if you have something like a concrete, right, you might have a process zone size which is on the order of the size of your test specimen, or the thing you're trying to simulate. So if you did a classic phase field model in this setting, what you would find is that you would regularize the crack over that zone. Now, imagine that you're representing your crack by something roughly that size. You're probably not making a very good, it doesn't really make a lot of sense. You're not making a very good prediction here because you're just sort of smoothing things over a large area. So this is work by with me and Professor Dalbo's group and Rudy Gielen. And so we can go to these cohesive style phase field models where the energy is defined kind of this normal phase field form. You have a strain energy and you have a surface energy term. And what you find is that on the top you have sort of the classic phase field where the nose and the regularization are the same size. And here you have a cohesive zone on the bottom where now you can see your nose is just as long as before. You're keeping that process zone size the same, but your regularization is getting sharper and sharper. So you get a pointier nose as you refine your regularization in this limit. So that's an important way, that's the essential way if you want to capture quasi-brittle material in a phase field setting. And so on the right, we see sort of the effect of, there's some parameters in here, but you have a traction separation law that results from this model. And this is a model originally proposed by Lorentz some time ago, and it's, I think, slowly gaining a lot more popularity in the community, and certainly it's almost exclusively what we use these days for our phase field modeling. And so the key idea, if I can explain it briefly, is that in the phase field model, you have a way of degrading the strain energy, and usually it's just 1 minus d squared. But in this model, in the Lorentz model, the way in which you degrade the strain energy is actually a function of the length scale. So this is a little bit uncanny. What this is telling you is that if I give you a length scale, you're going to change the local constitutive behavior. But it's done in such a way that it's consistent so that you get a clear, critical stress and a clear energy release rate. So it really is effectively, at least in 1D, a cohesive model. In 2D, the interpretation is a little harder, but in 1D, it's certainly equivalent to a cohesive zone model in the limit as the length scale goes to 0. So this is just showing some results and showing this, highlighting this ability. So if you have a large regularization length on the left or a sharp regularization length on the right, you get the same traction separation law. And this is a problem which the bar is long enough, you get a snapback effect. But you can see essentially the problem is insensitive to this, almost completely insensitive to this regularization length, thanks to Rudy. And you can see on the right sort of the profile of what the phase looks like when you have a very large phase length that's wide. And as we decrease that regularization length, it gets sharper and sharper. So we get a very sharp crack, but always maintaining that same cohesive behavior. So that's the takeaway. And then, I'm trying to give this a name. So this is a tough thing. So typically when we think about convergence, what Sandia wants is Sandia wants to be able to predict fracture in a way which is mesh convergent, because this is important for credibility. This credibility is a all-encompassing word we use for V and V and UQ, and so we want to have credible predictions. And so the idea that if you change your mesh, all of a sudden you get a different answer, hurts credibility arguments. And so the idea is you want it mesh insensitive. So in these phase field models, we have two senses in which we're mesh convergent. We converge both in terms of refining the mesh, but also in terms of refining the regularization. So I call this regularization convergence and then mesh convergence. So there's two concepts. You want to be able to converge in both settings. This is just another example of a stable crack growth problem, which the solution is mostly insensitive to the length. We've also implemented this for dynamic problems, and you can see that you can get crack branching automatically. There's really no difficulties there. And then you have a G sub C parameter. So if you were to increase that, for example, you would transition from branching to non-branching. And so you can capture kind of all the phenomena you would want and expect out of a quasi-brittle material in dynamics. And also, again, mesh sensitive and insensitive to the length scale. So this, just to give credit, this is a sort of a list of relevant work here. Of note, I will also mention that Nicholas Moyes has a sort of a related method called a thick level set method, which is also very promising. And then more recently, more general versions of these cohesive gradient damage models have been proposed that are very interesting. I also want to point out that even if you're modeling a brittle material, there may be a lot of compelling reasons to use this Lorentz-style model. For example, and this is, again, work out of Professor Dalbel's group, for example, if you have an anisotropic material model where your properties are different in different directions, the normal phase field model would predict that you would have a different regularization length depending on the direction in which your crack propagates. And that's sort of unappealing. And so by adopting the Lorentz models, you can decouple, again, the length scale from the regularization length scale from the physics you want to capture. And the same is true for heterogeneous material interfaces. If you're propagating through a material and the properties change, what you don't want to see, which you would normally see with a phase field model, is a change in the width of the phase field. So and then, again, another similar arguments for UQ. If you have statistically varying properties, you want to keep that length scale constant. So I wanted to just spend one slide. I could emphasize this more, but I just wanted to spend one slide pointing out that recently we made this connection between phase field and peridynamics. And so in phase field, the argument is you have this integral approximation of the surface energy. In peridynamics, you can actually do the almost directly analogous thing, and instead it becomes a double integral. And you can follow the same logic where you minimize an energy, and you have a peridynamic version of surface energy. And with this connection, what you can find is that you can take any model from the phase field community and essentially port it directly into a peridynamic model. So what we've done here is we've taken the Lorentz model that we liked in the phase field setting and adopted it in the peridynamic setting, where it retains the same advantages of where if you have a quasi-brittle material, we're separating this horizon size from the physics. And so there was a Besant pointed out not too long ago that, Professor Besant, that in peridynamics, the classic bond failure models, they have this coupling between the dispersion. If you have a peridynamic length scale, there's a certain dispersion that implies. And so that's coupling with the fracture criteria. And so that's a little uncomfortable that you're tying these things together. But the point is, this is not a fundamental limitation. If you adopt sort of these ideas, for example, from phase field, cohesive phase field models, you can separate the dispersion length scale from the fracture length scale. And therefore, some of the main criticisms of that is sort of mitigated. So this is just an example of that happening. All right, now we're getting on to the challenging part. Okay, ductile fracture. So it turns out at Sandia that most of the problems we care about are ductile. So there are applications in these other areas, but predominantly metals. Metal failure is the thing that we're interested in. And so up to this point, I haven't even talked about metals really, except for the fracture challenge, obviously. And so then the question is there a way to extend these methods to ductile failure? And so this is some of our progress. And of course, this has been proposed by others. Professor Wiseman, I think, was one of the first, and then Meehy and Borden sort of shortly thereafter. And they have proposed models for ductile phase field modeling. And so we're looking at those, and we're trying to kind of understand what it means to have a ductile phase field model. And so we're thinking about it this way. I'll just describe our thought process, is that when you have a plasticity model, you have an additional length scale that comes in. Because you have a yield strength, and then you have your fracture properties, and the dimensional scaling tells you you have this length scale, this plastic zone size. And so the question is, like, now we have this phase field length and this process zone size. How do those two relate Are they decoupled? Are they coupled? What do we do there? And so this was inspired by some classic work by Tupek and Hutchinson, where they did this analysis with cohesive zone models in the presence of J2 plasticity. And they were studying instead sort of the ratio of the cohesive zone length to the plastic zone length, but it's an analogous thing. And they showed that as you change these ratios, you get different R-curve behavior. So I'll take a minute to describe the R-curve. So the R-curve is this idea where you're doing a compact tension specimen, and the initial energy release rate is normalized to 1. And as the crack propagates to the material, as plasticity builds up, the effective toughness of the material increases. And so you get this R-curve behavior where your energy release rate has to increase, and eventually tends to steady state out at some point. And so that's what this is showing, is that for different choices of these parameters, you toughen up and then steady state out at some level of K. Okay, so this is probably too much equations, but these are details of the model just for completeness. But the idea is that, okay, in the plasticity setting, we have mechanical free energy and fracture free energy, just like before. And our model is that the mechanical energy is the elastic energy and also the plastic work. And the fracture free energy is sort of the standard threshold-based phase field, for those of you aware of the threshold model. We found that it's essential to use these threshold versions. If you aren't aware of them, we can talk later, but that's a key ingredient for these that we found. And then finally, some flow rule. So in order to sort of assess or validate what we're doing, we set up this so-called surfing boundary condition, which is again from Borden and Hossein. And the idea here is that we're going to apply a far field K field. We're going to ramp it up, and as time goes on, we'll translate it. And hopefully that's going to induce a propagation of the crack along X, okay? So you can see this is the representation of the boundary conditions. We're sliding the boundary conditions along in order to drive the crack with it. And as we're doing that, we're computing a J integral in order to actually figure out what's happening. So this is sort of the picture of what happens. We have initially this plastic lobe that forms, kind of like the picture I showed before. As the phase field crack starts to propagate, it ends up reaching the steady state, as we mentioned before, where the plastic zone size stays about the same, and then we see that our phase field is sort of resolved within that plastic zone to some extent. So this is trying to get some intuition. And what we find is we get sort of the same kind of qualitative thing that Hutchinson showed with cohesive zone modeling, which is that we can extract R curves, in this case J R curves, which is the J integral version of an R curve. And we can see that depending on how we choose the length scale, the regularization length scale, we predict different R curves. So what does this mean? This means that our regularization is not decoupled from our physics. In fact, our regularization dictates our physics. Our R curves are a function of our regularization length scale. So this is very different than the cohesive model I was describing before, where there's a decoupling between the physics and the regularization, which is essential. And so this is an experiment comparing this to experiments. We're able to choose the appropriate regularization length scale to capture the experimental force displacement curves. But we're not sure yet. This is still work in progress. We're not sure yet whether or not this is going to also capture the R-curve behavior that we want. And furthermore, like I just alluded to, it does not converge under regularization. And so I think that's a big challenge. This is one of the things that I think is the most challenging and limiting things of these phase field models for plasticity is this coupling between the length scale and the physics. And I think we need to find ways to decouple those two, and sort of inspired by Lorentz. And so that's the direction we're going to be going, and hopefully not too many people scoop us. And this is just showing that we get convergence under mesh refinement, but again, no convergence under length scale refinement. All right, last one. How much time do I have? Oh, I got to slow down. Okay. All right, so the last one is a bit of a transition. So we also want to model not just sort of quasi-static ductile behavior. We also want to model the response of materials in sort of extreme environments, very large deformations. And so that is a very challenging thing to do numerically, right? You have to have a method which is very robust to large deformations. And so what we've been working on recently, this is work with Jay Custer and J.S. Chen, is that we've been essentially implementing an RKPM into our code, but an RKPM which is modified in such a way that we can apply directly boundary conditions and overcome some of the sort of practical limitations for RKPM. So it's an RKPM sort of on a mesh, okay? And so what this buys us is a method which is actually sort of remarkably promising in my view, not that I'm biased, but So Jake has shown this in his talk earlier this week, that we get very good coarse mesh accuracy for a given number of elements. We're comparable to any element we have in Sierra in terms of cost per accuracy per cost. It's very efficient overall. The runtime for a given mesh is about comparable to a linear TET element. So there's almost no overhead. Usually mesh-free methods are sort of considered slow, but we've shown that this is not necessary. We actually have a method which is just as competitive as the other element formulations. It's also very robust under large deformations. You hit it and deform it, strains of 14 we've seen, right? Not 0.14, but 14, right, robustly. And then the last thing that's probably the main motivation for this work in the first place was insensitivity to bad aspect ratio elements. And so one of the big things at Sandia, in addition to fracture, is a huge challenge for us. One of the biggest challenges is that meshing is really hard. And when you mesh, you get bad elements all the time. And so we want a method which can take bad elements and still have it be a computable, analyzable solution. And so what Jake's shown is that with these approaches, if we can use the mesh-free shape functions and we do some aggregating with some details, we can actually take sliver elements and compute on them with very large time steps. And so there's a lot of compelling reasons to do all this. And so this is sort of an example compared to a TET element and then our formulation. We sort of at coarse meshes, we nail sort of the exact, or at least very refined version of that problem. This is a little bit unfair. Everyone knows that TETs are kind of locking and not very good, but the point here is that it works. And so we're compelled to try to go into this mesh-free arena, but unfortunately there is a challenge. Oh, sorry. One last thing. I wanted to show just an example of kind of how robust this can be in a total Lagrange setting. So, I mean, it splashes. This is a faster velocity than the normal Taylor impact. Do it again. It's a little quick, but it puddles up. And in fact, we can even run it at even faster velocities. I don't show the movie, but this thing just puddles almost to a straight line, and it's still running. So it's not like a time step is tanked. It's still running robustly. So this is like very interesting for a lot of applications for us to try to have a really robust element that can handle these large deformations. Okay, but we want to do fracture again. So let's try fracture. How are we going to do this? We're going to do element erosion or element deletion, whatever you call it. So when a mesh-free particle reaches its threshold, we're going to kill it. All right. And we do this is a compact tension specimen. We pull it, crack runs across, we get particles. Okay. So this is my tail. So back when I was a grad student, I was working in paradynamics at the time, and I presented some work to the Navy, and I showed results where I'd captured the terminal ballistic velocities for a certain experiment by calibrating my model, right? And so I showed the results, and you get particles just spraying away. And one of the kind Navy guys in the back said, why is it with all these mesh-free methods, all I see is particle spray? And so from that day on, I've sort of been on a mission to say, okay, well, like, what is it that's causing this particle spray, and what can we do to, because it's not really physical. I mean, there's some cases in which you do get particle spray, but it's usually, you're not resolving it or anything. So what is it that the numerical method that's causing this particle spray? Why can't we keep things together? Because there's compelling reasons to want a mesh-free method, but this is sort of a arguably unacceptable solution for a fracture. And you can see as you refine the mesh, right, you get very different response. It's very noisy. You get a different failure force depending on the mesh resolution. So let me just describe real quick what I think the issue is here. And so this is a bunch of particles, and we want to cut it in half, right? Just conceptually, we're not doing any physics. We just want to cut it in half. What does it require to cut in half a mesh-free method? Well, let's look at the middle node. It's purple now. And that's his kernel, horizon, support size, neighborhood, different names for different communities. And all those nodes in that circle are sort of interacting with him. And so he wants to separate his connection with everyone to the right. So what he has to do is every particle on the right of him has to die, has to go away, right? Because we're doing element erosion. And so that means that guaranteed, at the least, you have elements disappearing or particle spraying on the order of the length scale in this problem. And so that's sort of one explanation for why this particle spray is happening. And so we can make an analogy. Okay, well, there's a bunch of communities, lattice particle methods and bond-based paradynamics, where this issue doesn't seem to happen. And so in this setting, what they have is they have a bunch of nodes, and in between them they just have springs, just springs between the particles. And what you can do is you can just cut one spring at a time, snip, 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 and get a very clean, perfect surface, right? So this all kind of works pretty well in these settings, right? So the question is, can we use this same idea? This is something I've been working on for a while. Can we use the same idea of cutting the connectivity with the stabilized RKPM method? And so, okay, the answer is no. So, so we just try the simplest thing. When it reaches some threshold, we delete the interaction between them. We just drop it off. Okay, and we get kind of the same, almost the same thing. And maybe it's a little better, but if you look closely, you still get a lot of particle spray. There's a lot of noise. There's a lot of noise here, and you can see the force displacement curves. You just get chattering oscillations. And so this is comparing sort of the depth one versus the cut one. It's kind of didn't really bias much, unfortunately. So for part of my thesis, I proposed something like this, and yeah, I guess it didn't work. So it's too bad. So let me try to explain what's happening here. So imagine we have a mesh-free method where we're computing strain at this node here. So the strain at that node depends on the displacements of some particles around it. And then we have a material model, in this case, say a simple plasticity model, or whatever material model we might have. And we want to sort of non-intrusively change that material model to get fracture. So the idea is we have existing material models, and we want to change it to fracture. And so with the method I just proposed, what you would do is at some point you would just cut that bond, cut that interaction, cut that connectivity, and it's gone. Well, what happens? Well, if you look at, and you plug the resulting strain into the material model, you evaluate the resulting force, and you look at the forces along those connections, and you see that it hardens up, and then the red one is the one I cut. It drops to 0. That's what we expect. But all the other connectivities, forces to them, also drops. So you fall off the yield surface, and you get this pretty hard instability. That's the purple here, right? So by cutting one connectivity, you've affected everyone else pretty dramatically. And so this is sort of an unstable thing. Now you're coming off the yield surface, you have to harden back, you have to extend back up in order to get back on the yield surface. And there's also analogous things which can happen in phase field models, which we're going to get into. But again, there's this connection between phase field and sort of this mesh-free setting where you have to be conscious of this issue that you, as you decay things, you have to decay things in the clever way so that you're not just driving oscillations in the system. So the idea is super, super simple. I'm sure people have done it before, but I'll just articulate it. I haven't seen it, so I'll say it. I just want to think of the force between those two particles, and at some point I reach my threshold, and I just want to decay them slowly, like a cohesive model. And I want to decay them over some opening displacement, again, like a cohesive model. So I have my length scale. I put a length scale on the model now, the opening displacement. I reach my threshold, I gradually decay my force over some opening displacement. Simple. Now, I'm a big stickler, I don't know what was wiser there, apologize for that. I'm a big stickler for thermodynamics and the principal virtual work, as people who know me. And so doing that is a violation. So it turns out if you're going to do something on the force side, you had to have done something on sort of the strain side. And so the way you do it here is you can think that the contribution from the bond as it's decaying slowly tapers off. It doesn't take away its strain at any one point, but it takes away all increments, any additional increments of strain from that connectivity go away. And what results is now in the same sort of model problem, we're going up the hardening curve, we reach our threshold, we cut. The one that's cut follows this traction separation law down. The ones that weren't cut, okay, they're not unaffected, but instantaneously they're not. They're still continuous behavior, and everything runs slowly. So now we can retry. We can retry what we've done before. Particle erosion again, spray, lack of convergence. Cohesive particle method, which I'm calling it. I think that name exists, so I'll probably find a new name someday. And we see that we get a crack that propagates across. There's no particle spray. There's some evidence of resistance in this, right? As opposed to the crack just running unstably across. In this case, it's sort of gradually evolving and much smoother. Now, I mean, it's not perfect, but this is early days. And so if we compare the low displacement curves in this situation, we can see that the other strategies, cut early, they're very mesh sensitive. In this case, we get sort of the clean. This is what you see in experiments. It comes up to a peak and then decays off as the crack is open and propagated along. And then we try to do mesh refinement, because convergence is ultimately what we care about here. The story here is not where it needs to be yet. I think the claim is that for the last 3 levels of resolution, the solution is very insensitive, but making claims about convergence is strong. But we do see evidence of stable crack growth. There are some mechanics here. As you refine the mesh, you're not seeing this dramatic decay in the maximum force. You're seeing sort of, reaching sort of a steady state value. So what we think is happening here is that what's kicking in is the G sub C turn. There's essentially a cohesive model behind the scenes here. And so the G sub C turn is kicking in, and our threshold for crack propagation is based on that as opposed to the normal stress criteria. And so the reason why this is not maybe where it needs to be is right now we're running these in explicit dynamics. I think running them implicitly is going to help a lot. You see a lot of dynamic effects. But then the other issue that I'm alluding to is that you're chasing the singularity, right? You have an existing crack, 1 over root r singularity. And so we're not doing anything to address that. We're just trying to get a sort of practical method we're not trying to get optimal convergence rates. We're trying to get any convergence rates. Bar is lower. And so this makes this a little tricky. So there's some balances and trade-offs in this, right? All right. And so the last challenging problem that I just wanted to show off, because I always like to end talks on a sad note. So we have this ductile steel problem, and this is one of the internal Sandia fracture challenge problems that weren't open to the community, but it's shareable. And it's a ductile steel, and it's a lot of shear. So the shear is going to be order of 1. So this is where we kind of think we need these sort of mesh-free methods in order to handle the very large localized deformations. And it's very challenging both numerically to get this to run robustly, but also very challenging from the constitutive modeling side to get the behavior right. So I'm not even going to pretend to do that here. I just want to see if my method converges. And the answer is it doesn't. So there's not really any evidence like we saw in the last case of convergence. And the reason I think this is because we have a shear-dominated problem. We're likely trying to capture a shear band with ever-decreasing length scales. And so without regularizing the shear band, we're in trouble. So this, yeah. So I'll play it. Sorry. That's going to help. Sorry about that. And so this is an example. So what you see for sure is that you get a very clean surface. You don't get the particle spray you might normally expect. So in terms of robustness and sort of the qualitative behavior, it's very promising. But you don't get convergence. And so again, there's going to be a shear band in there that we're not regularizing. And so this brings up a distinction. And all this work here, I've been talking about regularizing a crack, right? What's the length scale of a crack? Well, a crack is sort of 0 thickness or maybe roughness, right? And so we want the regularization length scale to go to 0. But for shear bands, there's a physical length scale. So this is a different kind of regularization we need. We need to regularize the actual length scale in a shear band process. So what we're proposing is that we actually need 2 regularizations, one regularization for the crack creation and one which is separate from, which is the shear band. And this is sort of similar to what Wiseman's group has done, and other people have pointed this out, but we're also trying to explore these kind of things. So I'm finishing up. So the summary is that fracture is an important problem for Sandia. We really want convergence in order to improve the credibility. Although we don't need it to make predictions, it would be really nice to have. We want convergence. I'm arguing we want convergence not just with mesh, but also with the way in which we regularize. We should not be sensitive to the mesh or our regularization choice. I would summarize by phase field methods are pretty effective. They're very, very promising and work pretty well for brittle and quasi-brittle materials. I think for the community, in my view, there's been a lot of work in the phase field plasticity, but I think more work needs to happen in order to decouple these length scales in particular, and also to incorporate realistic constitutive models. Right now, it's always sort of taking a simplistic constitutive model and phase fielding it, but we would ultimately need to take any material model, such as the ones we already use, and be able to regularize those. And so those are some challenges, for sure. And the last thing is that I touched on this new mesh-free fracture approach. It's a potential alternative. I think it's still new, and it has relations, of course, to peridynamics and other mesh-free methods. But the advantage is, right, we can handle these large deformations, and we can do things in a mass-conservative way. And so these are promising things. But overall, there's a lot of trade-offs, things to consider, and opportunities to improve. So with that, I'll ask for any questions.